Hello, my name is Mandy Rosengren. For those who just joined, I am an onboarding engineer here at Entopology, and I'll be walking you through how to design a cold plate within Entopology and some options that we have available. So some of the key blocks and learning outcomes that we'll have for today, we'll first put in a custom lattice structure into the fluid region of our cold plate and put that structure in. And then later we'll also use fins and we'll arrange them in such a way that you can see in this image here. But let's get started by just opening up a new instance of NTOP. And if you haven't already, please download the files in this lesson, as we'll be using that cold plate file, that Parasolid file. So I will open up a new instance of NTOP. And the first thing that I'll do is just import that file that I have. So let me grab that. In our cold plate training, it'll be cold plate, and I can just drag and drop that into my first section. And I can just type Z to center this in my viewport. So I've separated this into a couple different bodies just to prep for bringing this in to NTOP. So if we go into the block details, under properties, you can see I have 6 different bodies. So what I can do is also just double click on a body and right click to create that, that variable as well. So I'll double click on this body, right click, and convert CAD body to implicit body. And if I just type I, so I'm only viewing this, and I'm viewing this in low resolution. If we do a section cut, we can see that this is going to have, this is really our exterior walls. So we're going to have the fluid coming in, fluid coming out from these different holes, and then this is where they're mixing. So I'll rename this our exterior walls. And then I also have my inlet flow and my outlet flow. So I'll just double click and hold Control to click on these and convert them to CAD face variables. Not really key to at the moment for what we will be doing in that structure, but just for the end, having those different fluid regions and separating them can be helpful. So I'll just say this will be our inlet flow. And then we have our outlet flow. So I'll double click on these two and then right click, convert CAD body to implicit variable, and double click on that name to label this outlet flow. So if we see here, I also have a CAD body list. So I also have this implicit body list. So if we wanted to maybe Boolean union these all together, if we're working with these in other instances, then we might want to do a Boolean union. And instead of having this implicit body list, since this is already a list, I can delete that option. And I can even take this out of my outlet flow and place it in there. So now instead of having a list of 2 bodies, I have them as one. And this still shows for my variable that I have an implicit body list type. So I might want to change that to then instead implicit body. So just something to think about when you are working with multiple bodies, just being careful of those lists because they can create issues downstream. Like I said, we're not really using too much of this inlet and outlet flow, but a good thing to just to remember. If you are continuing to use that list, it'll create those list variables all throughout your workflow. So you either will have to change those, do a Boolean union, or something along those lines. So I'll do the same process with the inlet flow. So I can grab another Boolean union and delete our implicit body list. And then drag out that implicit body from CAD body, like so. So I see that 2 items in my list and place them in for my bodies. Then for our inlet flow, again, I'll click on that icon that showed implicit body list and just type in implicit body to change that. And bring that in to our Boolean union. So to reiterate, maybe I'll change my inlet flow also to a different color before we visualize this all. It's my inlet flow. I can go to my display and change that. Let's just make it red. And our outlet flow, we can change to maybe blue. So now we have our inlet and our outlet flow. We have our exterior walls, and the last item, that last body that I have will be our inner fluid region. So if I can kind of look at my properties list for my import part, and because our last body that we want to work with is fully kind of encased in the rest of these parts, I can't double click. So I have to drag and drop it from my properties list here. So what I can do is see the different properties or the different bodies that I've been working with. So I have 0, 3, 5, as well as 1 and 2. So the only other one that I'm missing is this CAD body, which is bodies 4. So if I type I can also see that's going to be that last body that I'm looking for, which is going to be that inner fluid region. We'll also be using these CAD faces, so it's also a good idea to have that as a CAD body variable instead of just converting it to an implicit body right off the bat. So I'll close these sections. Maybe I'll rename this title of our import part to cold plate. I'll double click on this and label this CAD fluid region. And I'll also convert it to an implicit body. So I'll search in my search bar for implicit body from CAD body, place that CAD body in there, and just also make this a variable by right click, make variable, and labeling this, I'll just say inner region. And the first thing that we'll do with this inner region is we're going to add that lattice structure. So we have our geometry section all complete. So I can hide all those inputs for those different blocks. And I'll double click on section 1 and just rename this geometry. And if you saw in my image that I had before, let me bring that back up. I have this wall that we're going to have our fluid kind of go around, and that's where we'll have our lattice or our fins going around that as well too. So we also need to add that wall as well. So sometimes, you can do everything within CAD. Sometimes it might make sense to do some of it within CAD, some of it within topology. It depends on kind of the different processes that you want to go with. So I'm doing this next section in NTOP just to show a little bit of modeling in NTOP as well. So I'll add a new section and I'll label this walled region. And for our walled region, I'm just going to create a box from corners for that. And I'll turn on the visibility of our exterior wall so we can see where those inlet and outlet flow is. And from the Create tab, I'll choose that box from corners. And I'll just drag and drop this to a location that I want. Maybe something like this. You can play around with the design that you want for the box. We could also use automation and using some of the properties to also create this box. But just to show an example, I'm just dragging and moving this so that I know that it's intersecting with the box that I have with the geometry. And we can see it's a pretty sharp that sharp edge. So we might want to have a little bit of a radius on there as well. And so to do this with something like this in NTOP is what we'll do is offset the body. So I'll do offset body. And I'm just going to offset this. Let's try by 10 millimeters. So it will be a bit bigger on either side. But now we'll also see that I'm going to have that rounding. I might want to maybe make some of this, that width maybe a bit smaller if I like this rounding that I have. And we can see that it is outside of our part. So it's not just in that region that we want, which is okay, because what we'll do next is a Boolean intersect of this box and our design space. So I'll right click and make this offset body a variable, and I'll just label this wall offset. And we'll actually use this in a little bit as well. So I'll show how we can use that, especially for our fins designs. So to create that inner wall that I had in those images, well, all we have to do is a Boolean intersect. So I'll do a Boolean intersect of our wall offset and our inner region. So if I type I to visualize that, we can see now that I'm only going to be having that blend radius on that side here. So we have that little bit of rounding that we want. And I'll right click and make this a variable, which I will label as inner wall. So I now have this inner wall. And if I look at my exterior walls and do a section cut, let's change that plane normal to be 0, 1, 0 and bring this up a little bit. We can see what that basically looks like. And what I'll also do is a Boolean subtract of this inner wall with our inner region to get that full fluid region that we're working with. So I'll do a Boolean subtract of our inner wall from our inner region. So now this is going to be the geometry that I'll work with for adding my lattices, for instance. So I'll right click and make this a variable, and I'll label this fluid region like so. So that was just setting up our geometry. The next thing that we'll do is add some latticing to help with that flow. And I'll add a new section and label this latticing. So with our latticing structures that we can do, we'll use our periodic lattice body. So I'll walk through this, not in a huge amount of detail. So if you are new to this periodic lattice body block, I recommend checking out our Intro to Latticing lesson and course to understand how this block works. But I'll just grab this periodic lattice body right now. And we have our unit cell, cell map, and unit cell parameter. So you could choose one of our beam-based lattices, for instance, those columns, if you wanted to have kind of those placed in different areas of our fluid region. What we'll actually do is use a custom unit cell. And I have that in our folder that you downloaded. So that's labeled custom gyroid unit cell. So I'll briefly bring that up. But basically with our custom implicit unit cell, this is what we will repeat across that structure. And when we're working with that custom implicit unit cell, you can put in a CAD body that you converted to an implicit body. If you have a specific design that you want to have on there, you can create something with InNTop. This is actually a kind of a variation of our gyroid structure. So this is using some of our field-driven design. And if you're interested to see how we use this remap field and take something like this wall TPMS and convert it into something like this, then I recommend looking at our intermediate fields course. We walk through process similar to this, where we are using our remap field to warp a design like so. But in this example, we'll just, this uses a custom block. So my input is that approximate thickness of my walls. And then it just creates that custom implicit unit cell and it outputs that unit cell. So we'll import that into our notebook to use as our unit cell. So I'll go to this plus button and import a block. And the block that I'll choose is that custom gyroid unit cell. So we can see that structure here, like so. And where I want to place this is going to be on this bottom face. So I'm going to also have to review that CAD fluid region where I have that CAD face. And I'm going to just do a single click on that bottom face, right click, and create CAD face variable. And I'll rename this bottom face. So this is going to be my custom gyroid unit cell. I can add that into my unit cell for my periodic lattice body. And because we already control that thickness in the unit cell, which we have as 2 millimeters, you can see that instead of having those 3 inputs that I originally had with this periodic lattice body, that unit cell parameter 1, which is our thickness, is no longer displayed. So the last thing that I need for this periodic lattice body is just our cell map. And I'll go to my latticing cell map and choose cell map on CAD face. And for that face, I'll choose our bottom face with a UVW count of 681. And for my height, let's first do 15 millimeters. And let's see what this looks like. And what we can see is this is actually going below our part. So what we're going to actually need to do, and the reason for this is because we'll have that height that's going to be normal to that surface. And since our bottom face, that kind of positive side is going to be below our part, we're going to have this height that is above our surface. But we want to go within this full region. So instead, I'm going to change this from positive 15 to negative 15. So now we have something like so. It's going to be within our entire region and place that into my cell map. So now if I type I to visualize only that periodic lattice body, we can see that I have now this custom gyroid unit cell that is now placed in every one of those cells like so. So we also want to trim this lattice body because it is going within some of that inner wall, for instance, that we have. So what we can do is just go into our lattice utilities and choose trim lattice body. For our lattice, we'll use our periodic lattice body. And for the volume, we'll use that fluid region. We'll keep it inside with a tolerance of, let's say, 0.1. So now we've removed that other areas that are not connected or that are within our inner wall have now been removed. So we have something like this. So now that we have this lattice structure in place, the last thing that we'll do is just a Boolean union. So I'm going to make this a variable by doing a right click, make variable, and label this lattice. And I'm going to do a Boolean union of our lattice and our exterior walls and inner wall. So I'll add another item to this list so that we can also include that inner wall. And if I type I to only see this Boolean union, we can do a section cut. And we can see like so, everything is put in place. So we have this first example of a cold plate. So I'll right click and make this a variable, and I'll just label this lattice cold plate. So that's the setup of our geometry in our walled region and how we could add a lattice. So you could play around with this lattice structure. You could create a different custom implicit. You could change that different designs. but this is just one example that we can create that structure in the fluid region. And if I go back to my PowerPoint, the next thing that we'll talk about is using fins and patterning those using blocks like our orient object, as well as rotating those fins so they're always facing that inner wall. So we'll talk about that as well. So we'll continue with that same file. We already have that geometry all set up. So let's go back to that. And we can hide that latticing section. We won't be using that anymore. And open up a new section, which I'm going to label fin array. So if you're working with this fin design, maybe you have a CAD file that you have that specific design that you want to work with. In this instance, I'm also using a custom block, just like how we had used for our lattice structure. And I'll open that up as well too. It's the CB fin design file. And I'll just show briefly what this does. So what this part does, it uses you can input a length and a width along the X and the Y axis for your fin. And it uses this block called create single face mesh. So this is not an implicit body. This is just that surface. It's just that single face mesh. And it basically creates it out of a set of points. So I just define these 4 points that we have, the 4 corners, in the right, they must be in the right order in order to create something like this. So we're going from left to right and then down and then back, and we can get something like this, and our final result would be this. But we can change that width and length to create a different fin. So we'll be using this as our example. We can quickly change that size of the fin if you wanted to try out different sizes. So the first thing that I'll do is import that custom block as well. So I'll click on, now it says 1 because we have 1 imported block. Import that block and choose that CB fin design. And I'll just type I so we can see that it's a little bit smaller than the rest of our parts. And zoom in, and that is what we have. And I'm going to change this instead for a length of 4 and a width of 8 millimeters. So this is going to be the fin that we'll be working with. So I'll right click and make this a variable, which I will label fin. And to place this along our, we can close our geometry tab and open that walled region because we'll primarily use this, these 3 blocks. So to place this along here, we're going to use random points on a mesh. And actually, I spoke a little bit too quickly. So we will be using this bottom face as well. So we'll keep that open just for now because we will convert that to a mesh to place a set of points where we would place our fins onto that face. So in my random points on mesh block, I'm going to use our mesh from CAD body. And I'm going to use our bottom face. And now we can close that geometry section and see that we've placed points everywhere along that face. So if I had done that inner wall, that inner geometry within CAD, and then I had a CAD face that was only this region, then we wouldn't have those points there. To remove these points from the section, there's a couple ways that we can go about it. So we also could, instead of putting in our random points on mesh, we could use our remove mesh faces by body and just put in this mesh that we're working with. And the body that we are going to use to remove parts of that face would just be, let's say, that inner wall or that wall offset, which overlaps it. And we can see that it gets certain regions here. We would also have to, so if we see if I don't reverse this, if I look at my wall offset, because we only have a few triangles created, it actually doesn't remove the entire region. So what we would also have to do is remesh the surface, place that surface into there, and control that edge length. So if you had a really small edge length, I'll just still keep it relatively a good size of 1 millimeter. and a triangle. It may take a little while to run, but now instead of having just a few triangles, we will have, you can see a lot of triangles here. And when we put this in the remove mesh faces by body, it'll select only where those triangles overlap the body or vice versa. But this can take a little while to run. We saw that remesh surface, and there is another way that we can go about this without having to remove portions of that mesh and remesh this then like so. So I'm going to just place this mesh from CAD body into our random points on mesh, and we will remove those points after we place them onto that mesh. And I'll delete our mesh faces by body and remesh surface. And I can make my point count a variable. Maybe I want to change that. And I'll just label this approximate number of fins, because we will be removing some of these, so it won't actually be the exact number, but we'll just start with this 100. And I'll right click and make this random points on mesh also a variable, which I'll label as points. So another way to remove all of these points is using our filter points by volume block. So I can type that in. We can see that this also has a double line. So just like our fin design, this is a toolkit block. You can right click and you can export this block and see how this was made, this process. And this is a toolkit block because it's already within our software. So this is just another option that you have in here to save some time. So what our filter points by volume block does is you can import a set of points, place those in there. So that'll be our random points on mesh block. And then we can place them into this volume and choose to have anything that's inside, outside, or that boundary. So I'll remove our point list, place our points in there. And for the volume, I'm going to use our wall offset because we definitely know that that overlaps that mesh. With our inner wall, because it's right on that edge, it might have some trouble selecting those points. So the offset body will be a better option for this. So I'll place it in there, and you can see it's highlighted the blocks that are inside. I want to keep only what's outside. So I'll choose what's outside of there. And type I to see that now this is going to be where I'm going to place my fin on these points. So I'll right click and make this a variable and label this fin locations. So I've defined where I'm going to place these fins. I also have to think about how I'm going to angle them. So I'll place my fins using an orient object block. So I'll search in my search bar for that orient object, which will take in an object, which will be that fin. It can be an implicit body. It can be really any type of object. A mesh is what we'll be working with, any type of spatial 3D. So if I look in my information tab for my fin, we can see that my mesh can also convert to a spatial 3D. So I'll place in fin for that option. Our source plane, this is going to be if you look at our plane or our fin, I'll type a Z to focus on this. I want to place this on to all of those points so that it's in the center of that that X and at the minimum point for that Y, and then it can just be at that centroid for the Z. I mean, the Z would just be kind of at that 0 location. So for our source plane, I'll put in a plane from normal. Our plane from normal, I want it to be kind of sticking up from there. So instead of it being 0, 0, 1, I want this to be 0, 1, 0. So we can see it's normal at face. And let me turn around my view so we're looking at this from the top. So that's the right orientation for my source plane. And then for the location, I'm going to use some of those properties within my fin to define that. So for origin, I'm going to define the X, Y, and Z separately. So I'll type in point. So I can control that X, Y, and Z. For my X, I can go into my properties for my fin and go into that bounding box. And I want this to be in the centroid X. So that would be 2 millimeters. But maybe if I am changing my fin length and width, this might be different. So I'll just grab that X so we can see it's in the center. And I can also define that Y in case I change anything as well too. Or if you're rotating this part in some way, then we might want to also define this. And we can either do that by going back to those properties and taking that minimum point for the Y, or we can type this right in. So I'll type in fin, click on that option, and choose to go into that bounding box and choose that minimum point for the Y. So it gives us that same result, but again, it's connected to that fin, so sometimes this can be a better option. And I'll just keep Z at 0. So that's our source plane, and I want to also define my destination plane. So I'll type in also a plane from normal, and I'll actually make this a variable, which I'll label oriented planes. And we can see it's already shifted it. So if we look at this first plane that we have, it's going to be pointing out along that Z. And so that orientation of our plane has changed, and it's been placed right at that same location that we had our source plane. So just the same in the center of that plane that we have for our oriented planes as well too. But we want to have them in more locations than just this one spot. So I'm going to use my fin locations for those. So for my origin, I'm going to choose fin locations, like so. Another thing to note too, so I just had this error that popped up, which shows invalid input type. So just as I had been talking before about thinking about creating those variables, just being careful of the list versus not a list. So this fin location is a point list, and we actually do want to have a list of planes. We want to have a plane at each one of these points. But because I made this a variable when there was only one plane, I have a plane type and not a plane list. So I'm going to have to click on that plane and just switch it to plane list. And we can see I have now all these planes at all of those locations. The orientation, however, is not as I want it to be. So if we look at our orient object, we can see that they're like so. And instead, I want them to all be as if I have it in, let me go back to my image again, so that they are all facing that inner wall. So what I'll do to create that, there's a couple ways that we can change that location and that orientation. And so what we'll be changing is this normal in our oriented planes. And what I'll do, I'll go through this process first. If you've gone through some of our other orient objects, I'll show this option first and why we, and kind of the behind the scenes of how that works. So in the meantime, let's hide this orient object. We won't be really using that quite yet. And one way that we can orient our planes is using this closest point block. So if you are placing points on a specific part and you want it to be normal to that surface, you can place in that body. So for instance, let me hide some of these inputs. So that would be, for instance, our inner wall. We would place those points that we want. So those fin locations. And if we look at this, they've basically placed all of those points that we had and just arranged them on our inner wall. So it just brought those in here. And the reason you might want to use this is because if I go to the block details under properties, we can get that normal. So if we were placing this into our oriented planes as our normal, our fin locations would still be the original location, But now what we can see is that it has rotated around. However, and they're all normal to that surface. So you could play around with this option. Another way that you can create the same result is using our evaluate field gradient. So you can check this out here. So it's going to evaluate that scalar field at a specific location. And it works pretty similar to this closest point, but it would only give us that normal to the surface. It wouldn't bring those closest points. So if I put in my inner wall and my fin locations, I now have 76 vectors that I'll be working with. And if I place this into my oriented planes, we can see it gives us the exact same results. So that's another way that we can go about something like this if you don't need to have those closest points. So I'll delete that closest point, but just showing that kind of behind the scenes of how that works. So we're evaluating that field at the location, and this is what that normal to that surface would be. But I want my plane to be slightly oriented differently. So actually what I will do is use a cross product. So this is going into our math tabs. So we can play around with some of our vectors and change them. So I'll use a cross product, and I'm going to take in those that evaluate field gradient, those 76 vectors, and you can see kind of how they're pointed. And then I'm just going to put in operand B as 0, 1, 0. So now if I place this into my oriented planes, we can see how that changes things as well too. And from there, the last step that we'll do is we can use this for our plane from normal. We can play around with that cross product and change that as well to see how we can get a different result. But I'll actually use this with a plane instead. So instead of just defining that normal, what we'll do is define the x-axis and y-axis. So this one is going to define the x-axis. And we can see it's all at that origin point. So I'll bring in those fin locations. And we get something like this. And then for our y-axis, it's just going to be that evaluate field gradient. So what I'll do is hold control and just drag that into there. And so now I'm going to define that x-axis. I define that y-axis. So that's another way that we can define that plane. Instead of using a plane from normal, you can just use that plane and define the x and y-axis. And now we're going to have the plane. So its normal is facing up along that y-axis, but we can see that the planes, especially in those corners, we see that rotation happening. And if I remove this plane from normal and delete that, place in this plane instead, and view our oriented objects, we can now see how our fins are oriented, like so. So we could have used maybe that plane from normal that we had before and just use this evaluate field gradient. And based on how that plane was created, we would just have to change that source plane to get the correct results. So instead of having this source plane so that it is at that minimum point in the y, like so, we might want to change that normal, change how that is placed on here to get, if we just wanted to use maybe that one evaluate field gradient. But this is another way of how we can create something as well and have that oriented around using a plane. So that's our orient object, and using that evaluate field gradient definitely can be a few extra steps than that closest point. So you might just want to use that option as well. But now that I have this orient object, so I'll type I so we just see these fins, I'm going to merge them all together. So I'll do a merge meshes. And since this is already a list, I'll delete our mesh list and place in this orient object. So now I have one item out of all of these. But again, this is not with any thickness. So what I'm going to do is thicken the body. And I'll have to convert our merged meshes into an implicit body. So I'll just do a, in our body section, I'll do implicit body from mesh, place in our merged meshes. And for our thickness, I'm going to do 4 millimeters. And I'll make this a variable so we can change that. So just looking at this thickness, maybe it's a little bit too thick. Maybe I want to change that to 2. You can play around with those different options to get those different results. And I can also click on this icon for thickness and change it from scalar to scalar field. So maybe you want to have fins that are thicker in some regions than in others. You can use our field-driven design for that. So I'll right-click on this, this block and make it a variable, that thicken body block. And I will label this final fins. And now that we have this fin design, we'll just go to that next step, which is doing a Boolean union of all of the options. So I'll add a new section, label this Boolean operations and final body, and use a Boolean union to combine our final fins, our inner wall, and our exterior walls, like so. And I can do a section cut to see how that looks. And you might want to add a little bit of a blend radius as well. It looks like there's already a blend radius. That's because I'm viewing this in low resolution. So if you actually do want that blend radius, you might want to add that in as well, like so. We can view this with a different plane from normal, a plane normal at 0, 1, 0, for instance, to see how that looks. And again, you can change the number of fins. Let's try 150, see how that looks. You can change that length and width to quickly go through these different fin designs. So I'll right click and make this a variable, which I will label our final body. And then if you're running some type of simulation as well on this, you might need to also have that inner flow volume. So what you can do is a Boolean subtract. And I am just going to take our fluid region and subtract out those final fins that we had. And we could also add in that inlet and outlet, for instance, as well. But then we can see this is just going to be that fluid region that we have. Or I can also do, just to ensure, with especially for using that rounding, we could also do a Boolean subtract of kind of everything we're using, and then just doing a Boolean subtract of our final body. So I'll right click and make this a variable and label this inner flow volume. So that's another way that we can create a cold plate like so. So those are the two different workflows that we will walk through step by step in today's session. So if you're looking for the resources, you can check out these different links and different videos. The last thing that I'll just talk about briefly is you can learn more about it in our third resource, which is designing a semiconductor wafer cooling disk. And I'll just briefly bring that up as well. And you can find that in your list of resources in that file. But I like to bring this up as well too, because if we look at the final result of the sample disk I have shown, and I do a section cut, let's change that plane from normal, we can see that that location of these pins I've created, this branch lattice body, they're not all in the same place. And so another key aspect that you can use, we've talked a little bit about field-driven design briefly today. What you can also do is use, for instance, a temperature field or CFD data to generate where you're going to place those fins or pins, for instance. So in this workflow, and you can learn more about this in our data-driven design training videos, for instance, or intro to field-driven design as well. And I just import this part. I have my bottom face disk and my top face. And the way that we're able to place these columns as so is by bringing in a temperature field. So this is a scalar point map. We close this and just view this. So this is going to be an example of this temperature field that we have in different locations. So that red is those areas of higher temperature and then those areas of lower temperature. And then from there, we can use this in our ramp to define where we're going to place those points. So I convert this to a field. So we bring in that scalar point map. And then we'll just use field from point map. And if I type F and change that plane normal, we can see I now have this field. Like so, it's only going to be in that location. But what we see, let me re-show that. If I change from my distance field color map to my turbo, we're going to just have a field that we can work with to place our points in different locations. And you can also play around with that interpolation. So if you wanted it natural, linear, near, stereocentric. And then for our ramp, we can place this in here. For our minimum and maximum temperature, we can say what we want that point spacing to be, which is going to be 10 millimeters and our outmax of 3 millimeters. And so then when we're creating those random points on a mesh, as we had done with this bin in our previous example, we can place this in for our spatial weighting. So instead, if I remove this ramp, if we look at the random points, we can see it's even throughout that face. However, if we put in that ramp spatial weighting, we can see that in those areas of higher temperature, we're going to have that closer spacing, and areas of colder temperature, we're going to have those spacing as well. So then from here, we can use this to create our branch lattice body if we wanted to create these pins. So just placing in those starting points, and then we're just translating those points upwards to get a column like this. You could also use this for the orient object, and eventually we get this sample disk like so. So that's an example of how we can use field-driven design to generate some of those locations for where we're going to place it in the cold plate, for instance, as well. But that's really the end of our session today and giving some information on cold plates. There's definitely a lot of areas that you can further explore as well, using that simulation results to drive your design for your cold plate. If you have any questions, feel free to reach out to our support at entopology.com, or you can reach out to onboarding@entopology.com, or check out some of these other articles and videos that we have along cold plates. So thank you for coming to our training today, and yeah, have a great rest of your day.